Here is what the IB curriculum expects you to know about vectors and scalars. Notice that this is topic 1.3.1, 1.3.2, and 1.3.3. These particular things that you need to know are directly from the IB syllabus. So they expect you to understand the difference between vector and scalar quantities and give examples. They expect you to be able to add and subtract two vectors using a graphical method, which we'll show you here today, and being able to resolve vectors into perpendicular components along chosen axes. We'll deal with that a little bit today and more next class as well. Okay? So vectors. We'll quote here. Victor, Vince Crunch, Roger. Remember that? You guys see that movie? Yeah, classic movie from Airplane. So vectors pop up everywhere in your life. The thing about vectors is that when you're doing math with vectors, you have to deal with them differently than you're used to doing math. You do not do arithmetic with vectors, okay? So, for example, let's look at this idea of taking a plane trip with a headwind and a tailwind versus without for a second. Okay, so again, you can't be linear, you can't think traditionally when we're thinking vectors. So let's get back to just our traditional concept of math. What is 1 plus 1? And this is not a trick question. What is 1 plus 1? 2. Excellent. That's what we've been telling you ever since you were in kindergarten, right? 1 plus 1 is 2. And that is true when we're talking arithmetic. When we're talking vectors, that may not necessarily be true, okay? Because if I'm adding a vector of 1 this direction to a vector of 1 this direction, what does it add up to? 2. So it's true. 1 plus 1 is 2. But if I take a vector of 1 this direction and add it to a vector of 1 that direction, now what do I get? 1 plus 1 is 0. And vectors, remember, vectors can go all directions. So what if I have a vector of 1 this direction and add it to a vector of 1 that direction? Okay? It's not actually 1. We have a triangle now. Okay? Square root of 2. Okay? Pythagorean theorem, 1 squared plus 1 squared equals all that other stuff, right? Okay, so this is why with vectors you have to be thinking about the direction and how to deal with that. Intuitively, you already have an understanding of how vectors work. Intuitively you do because you've probably been out running or biking or skiing or something when it was windy. And have you ever noticed when you're doing that, it happens to me when I'm biking most. So when I'm biking along and there's a wind, there's a huge difference between when the wind's blowing in my face and when the wind is blowing behind me. Have you ever experienced that? Okay? That is vector analysis. You have a velocity on your bicycle. The wind has a velocity. When I add those velocity vectors, if they're going opposite directions, it's very, very different than if they're going the same direction. Okay? That is basic application of vector analysis. All right. So let's just get into our definitions of vectors versus scalars. What is a vector? What makes something a vector? Magnitude. Is that what you're going to say? Magnitude and direction. Excellent. A vector has magnitude and direction. For example, what are some things that are vectors? Velocity. Anything else?
Running to the east.
Acceleration, force, displacement. Displacement, okay? Excellent. Those are all things that are vectors. Momentum as well. We will continue to study things that are vectors, where not only the size of the thing is important, but the direction is also important. A scalar quantity is something that can be described simply with a number, a numerical value, or a magnitude. Examples of that would be time, mass, electric charge, temperature. Those things are scalar quantities because they do not have a directional component to them. I can tell you the temperature and tell you it's 32 degrees outside. I don't have to tell you what direction it's 32 degrees. It's just 32 degrees. Okay, so when we're dealing with things that are vectors, how will we deal with them? One of the ways we will deal with them is graphically, which means basically drawing, okay? So we can represent vectors graphically by drawing an arrow. A vector can be represented by an arrow, okay? The length of the arrow will tell you the size of the vector or the magnitude of the vector. The direction that you draw the arrow will tell you the direction of the vector. It's pretty straightforward. I can also describe vectors verbally. For example, my displacement happens to be 4 meters, 30 degrees north of east. That would be one way of also describing a vector. 4 meters being the magnitude, 30 degrees north of east being the direction. So, vectors are represented graphically by an arrow. When I'm drawing a velocity vector, for example, I need to draw an arrow. And if all I do is draw a line, that doesn't count. Because the line tells me approximately the size of the vector, but it doesn't tell me anything about the direction of the vector. I need to add an arrow. Okay, there I know that my velocity is to the right. If I were traveling more slowly, I would draw it like this. If I were traveling more rapidly, I would draw it like this. If I were traveling in a different direction, I would draw it like that. Okay, that's how we represent vectors. Pretty straightforward. The other thing, in terms of direction, describing direction of vectors, we can describe them a couple different ways. Sometimes we will use cardinal directions, and if you're not familiar with those, try to get familiar. Okay, north, south, east, west. Okay, we'll do it that. Sometimes we'll say, oh, it's 30 degrees north of east, or 20 degrees west of south, something like that. Sometimes we will describe directions purely with a numerical value, a degree value. And just like in math, when we're talking about degrees, 0 degrees is right here on the x-axis. 90 degrees is the positive y-axis. 180 degrees is the negative x-axis. And 270 degrees is the negative y-axis. Okay? So to check that out, let's pretend I had a velocity of 47 meters per second, and I was traveling at 212 degrees. What direction would that be? Okay. Oh, gosh, I hate it when that happens. 47 meters per second, 212 degrees. No, come on. There we go. 212 degrees would be somewhere down here. What would this angle be? Oh, no, you don't. 212 degrees?
32 degrees.
Okay. Now be really careful. If you describe that vector as 47 meters per second southwest, that would be incorrect. Okay? Okay? Because south, it would be 32 degrees south of west. If you just say southwest, that is a very specific direction, which is halfway between south and west, which would make this 45 degrees. Okay? So please be very specific when you're describing the direction of your vectors. Okay? All right. Back to here. Okay, let's look at another question here with planes and winds. Will a plane that is flying with a 90-degree crosswind, the wind is blowing perpendicular to the direction of travel of the plane, will it fly faster, slower, or the same speed or same velocity as if there were no wind whatsoever? Okay, so let's look at it. Let's look at it and see what happens. So here's my plane. Okay, and now it's got a big tail. And it's flying this way with a certain velocity, v of the plane, okay? And now the wind is a crosswind. Okay, wind. So the result of these two velocity vectors, imagine what the plane's actually going to do through the air now. It's going to do this, right? Okay, that's the actual velocity of the plane now, the sum of those two vectors. Wind's pushing it sideways, plane's pushing forward. Notice this is a right triangle. The hypotenuse, therefore, has to be larger than any of the two sides, which means the velocity, the actual velocity of the plane plus the wind is greater than the velocity of the plane alone.
But that's totally not the same as the...
Let's get into vector addition. How do we add vectors? Again, we just talked about earlier that you can't necessarily add them as you would add numbers arithmetically unless the vectors are in the same direction. But let's do some vocab before we figure out how to add them. And the first vocab word you need to know is called the resultant. The resultant is the vector that results from adding two or more vectors. When you add two or more vectors, the vector that you get is called the resultant. So if you have a problem that says, find the resultant of these vectors, what it's saying is, add them together and tell me what you get. In order to find the resultant, you will want to draw vectors, and there's kind of two methods that are used commonly to add vectors. The first one is known as the tail-to-tip method. This happens to be my method of choice. I'll explain it to you in a moment. The second method is known as the parallelogram method.
But if
I prefer not to use that one, but that's just me. You might like that one better. I'll show you how they work in just a second. Okay, so let's look at this whole adding vectors thing. Imagine for a second I had vector A, and to it I wanted to add vector B. What would that equal? What would my resultant be? Intuitively, you can probably already figure it out, but let me show you specifically how you want to do it. Draw your first vector, A. The tail to tip method says now draw your second vector with the tail of the second vector starting at the tip of the first vector. So I'll start drawing vector B right here. I'll keep the direction the same. I'll keep the magnitude the same. Here's the big final conclusion thing that you need to remember. The resultant is the vector that goes from where you began to where you ended. That's your resultant. Ta-da! Okay, we've just added two vectors. A very, very, very common mistake would be to, oh, I hate when that happens. So a common mistake is to draw your two vectors like this, and then to draw your resultant like that. What's wrong with that? Okay, it's 180 degrees the wrong direction. The magnitude will be right. You'll get the right size vector, but you'll be going 180 degrees the wrong way. So remember to add, or when you're adding vectors, your resultant goes from where you began and ends where you ended. The second thing I want you to see is it does not matter the order in which you add your vectors. Just like in numbers. What's 2 plus 3? What's 3 plus 2? Excellent. So here's vector A plus B. I could just as easily done vector B plus A and gotten the same thing. Okay? Yes, for those of you that would like to see the parallelogram method, let me show it to you. You draw both vectors, vector A and vector B, okay? And then you make a parallelogram with them. Here's vector B, here's vector A. There's my parallelogram, happens to be a rectangle in this case, and the resultant would be the vector that goes diagonally across the parallelogram. It's pretty much the same thing, it just requires you to draw more vectors. All right. So, notice that when your vectors are in a single plane, this is easy stuff, right? Here's a displacement vector of 8 kilometers plus 6 kilometers, and hey, the resultant is 14 kilometers. I just added them up. That's easy because they're going the same direction. And even if one of them is going the opposite direction, it's still pretty darn easy. 8 plus a negative 6 is going to give me a resultant of 2. You with me so far? Pretty simple? Okay. Here's another way of kind of looking at a vector. You know, here's a vector to the east, a vector to the north. One of the things we're going to do is kind of do this backwards also. Rather than adding vectors, we will take a vector and break it into pieces that are perpendicular to one another. Okay, this is called looking for vector components. So if this was my original vector, sometimes what will be useful for me to know is what is the magnitude of that vector in one direction and another direction perpendicular to it, in an x and a y direction. And that will be information that will be useful to me. And we'll work on doing that as well. I'll show you how that works at a later point. Now, it doesn't matter how many vectors you add, you can still use the tail to tip method. Here's vector 1 plus vector 2 plus vector 3, and notice they use the tail to tip method. They started at some location, they drew vector 1 the same length and same direction as it is. They added vector 2 starting at the tip of the first, then they did vector 3 starting at the tip of the second, and the resultant goes from where you begin to where you end. And it still does not matter the order of in which you add them. I could have just as easily started with vector 3, gone down to vector 2, and then added vector 1, and I still would have gotten the same answer. Okay? Nick? Okay, great. Let's see. Here's just another slide showing you how to add vectors. Vector 1 plus vector 2, okay? Tail to tip method, or the parallelogram method, okay? But not the wrong method. Don't do the wrong method. That's bad, okay? Notice that that vector is going the wrong direction. That resultant is going the wrong direction. All right? You always draw your resultant from where you started to where you end. Okay. That's how you draw resultants. But the critical thing that we're going to be dealing with is how do you actually then calculate its size and its direction. So once you've drawn your vectors, we actually would like to figure out how long it is, or the magnitude of it, and its direction. If the vectors are perpendicular to one another, we will use the Pythagorean theorem. A squared plus b squared equals c squared to find the size of the resultant. We will use trigonometry to find the direction of the resultant. Right angle trigonometry, okay? So there's the Pythagorean theorem. Hopefully you're aware of that one. And trigonometry will just be SOHCAHTOA when you're dealing, most of the time you'll be dealing with vectors that are perpendicular to one another, okay? So let's try it out. Let's try it out. We'll talk about crossing the Gulf Stream here and see how this all works. Okay, Gulf Stream. Imagine this is Florida. Woo! Okay, there's Florida. And there is a city right about here that's called Fort Lauderdale. Fort Lauderdale. And imagine that you guys have all graduated and you're all living in Fort Lauderdale. It's awesome. You're having an IB Physics reunion, and one of you has gotten really successful, made tons of money, and bought a really huge boat, big old boat. So you're all out there in your bathing suits in the sun. It's Friday afternoon. You're drinking soda, and right, and you got your boat. And one of you says, "Oh man, it's Friday. We should go to the Bahamas." And then you're like, "Okay, cool," because there's an island over here in the Bahamas that's called West End. And West End is due east of Fort Lauderdale, and it's only 75 miles away. It's only 75 miles away. Oh, that is so close. We could be in the Bahamas so quick because my boat is so fast that it goes 30 miles an hour, which someone told me the other day that's not fast, but hey, it's a boat, all right? It's better than nothing. It's better than rowing. So your boat's going 30 miles an hour. Everybody's sitting there in their bathing suits like, wow, cool, it's Friday. Let's go to West End. Now, so you take your boat and you aim due east because that's where the West End is. It's due east of Fort Lauderdale. How long will it take you to make this crossing? 75 miles, 30 miles an hour. 2.5 hours. So you're thinking, wow, 2.5 hours later, we're going to be over in the Bahamas. We'll drink some more soft drinks and have a good time hanging out in the beach. It'll be awesome. So you start heading across, 30 miles an hour, 2.5 hours later, you're all excited. But 2.5 hours later, you end up running into a coral reef, ripping a hole in your boat, sinking, everyone gets eaten by sharks and dies. Isn't that horrible? Isn't that awesome? Okay. It's a great story. Okay, because there are coral reefs that extend north and south of West End Island, and the thing we didn't talk about that someone over here mentioned is there happens to be a very strong current between you and the Bahamas, and that current is called the Gulf Stream. It's a very famous warm water current that runs up the east coast of the U.S. And the Gulf Stream is a very consistent current. It tends to run at about 6 miles per hour. Okay, pretty consistently all the time from south to north. So for 2.5 hours while you were driving across, the Gulf Stream was pushing you to the north. How far north did it push you? Where did you crash? 6 miles per hour. Using basic math, we know it takes 2.5 hours to cross. The Gulf Stream's moving at 6 miles per hour north. Therefore, you crashed. The site of your deadly, bloody crash was right up here, 15 miles north of West End, and you all met a grisly, grisly end. Okay? So, now that you know this, where should you have aimed in order to get to West End?
15 miles south.
Okay, what would have made sense is to aim 15 miles south of here. And we know that it's 75 miles across, 75, okay? So now, using basic trigonometry, we can figure out what direction we should actually have aimed the boat. What trig function should we use? Okay? No, we want to use the trig. We want to use trigonometry to find a direction. How did you figure out tangent? Okay? So tangent, remember in SOHCAHTOA, tangent, that didn't look very good, equals opposite over adjacent. And those are the two sides of the triangle we know. So tangent of the angle I'm looking for equals the opposite side of my triangle, 15, divided by the adjacent side, 75. How do I take that to find and then find an angle? What do I do?
Second tangent.
Okay. Second tangent, inverse function. So go second tangent of 15 divided by 75 and tell me what you get for your angle. Now we won't die because you know you should be heading 11 degrees south of east. Yeah, or you could actually hold the steering wheel and look at your compass. All right? Now, this is real basic. Obviously, it's oversimplified. One of the things I want you to see, the next layer of complexity for this general idea, which you don't need necessarily to know for this class, but I think it's kind of interesting. There's Fort Lauderdale. Here's West End. If you really did this, you really aimed your boat 11 degrees south of east, okay? The Gulf Stream is pushing you, to the north, okay? But the Gulf Stream is just like a river in a river, okay? It's got, the current isn't consistent. The current is actually stronger in the middle and weaker at the edges. So this is what you would actually be doing. You would set your heading, okay? Here's the straight line across. Your boat would actually beat the Gulf Stream at first. Then the Gulf Stream would push you back up ahead of it, and then you beat it again, and you'd end up doing a sine wave across the ocean as you tried to get to your destination. That's kind of cool. Great. So please get comfortable with the Pythagorean theorem and SOHCAHTOA. You will be using them frequently, okay? When you have a vector and you want to figure out how the component in the x direction and the component in the y direction, you'll need to use trigonometry to do that. Or when you add vectors perpendicular and you want to find the direction of the resultant, you'll need trigonometry to do that. Okay? Again, a practice. Let's just say, for example, no, we'll practice that some more in just a little bit. Now, your vectors won't always be perpendicular to one another. Okay? Sometimes they won't be. And you can do some things to make them perpendicular and still use Pythagorean theorem and SOHCAHTOA, or you can also use the law of cosines. And I used to be unhappy about the law of cosines. See, I put a little unhappy face there, but I'm getting rid of that because I think the law of cosines is awesome. Okay? All right? The law of cosines, no, it is not in your data booklet. But here's what the law of cosines says. If I have a triangle, come on, if I have a triangle that is not a right angle triangle, imagine that extends out to be a little triangle, okay? And I know side A, and I know side B, and I know the angle between them, I can use the law of cosines to calculate the length of side C. And the law of cosines says C squared equals A squared plus B squared minus 2 times A times B times the cosine of angle C. Okay? It's not a terribly complicated equation, and it is, in fact, the Pythagorean theorem applied to all triangles. Because what do we normally use the Pythagorean theorem for? What kind of triangle? Right triangles, which would be what angle C? 90 degrees. Cosine of 90 is, what is it? 0. Cosine of 90 is 0. So when this angle C becomes 90, cosine of 90 becomes 0, and all of this goes away, and you're left with the Pythagorean theorem. Okay? So this is the Pythagorean theorem, just in a more general form. All right, let's do just real quick one little practice. Let's imagine that I have a velocity. Give me a number. Give me a number.
13.
Oh man, I heard 6 first was the first thing I heard. My velocity is 6 meters per second, and I'm traveling at 30 degrees north of east. My question to you is, how fast am I traveling in an easterly direction or in the x direction, and how fast am I traveling in the y direction? So I know one side of my triangle, and I know the angle. What I want to do is solve for the other two sides. Talk to your friends, talk to your neighbors, phone a friend, whatever you need to do. For those of you listening at home, you just missed how we did all that. But that's how we did it. All right, figure it out.